Welcome to Chapter 7 of the course. By now you've already learned a ton about building science, and in this chapter we're discussing a topic that can make it or break the comfort and efficiency of your home, your heating and cooling system. You've probably heard the saying that bigger is better when it comes to heating and cooling systems, but that couldn't be further from the truth. I'll break down why that is, discuss the different types of heating and cooling systems, along with some different features to consider, and what makes each type unique. Let's get started. Why the size of your HVAC equipment matters. As we've discussed before, in the past, homes were built without much consideration to air sealing and insulating them properly. This meant they needed big furnaces in the wintertime to offset all that rapid heat loss that occurred, and big air conditioners to cool and dehumidify all the hot, humid air that leaked inside in the summertime. And when I say big, I'm referring to the output capacity of the heating or cooling equipment compared to the square footage of the house. I'll come back to this point here in a minute. Output capacity for gas heating systems is measured in thousands of BTUs, or British thermal units. When you look at the nameplate on your gas furnace, water heater, or boiler system, it'll say something like 80 kBTU, which translates to 80,000 BTUs. Output capacity for heat pumps, geothermal systems, and air conditioners is measured in what's called tons, and 1 ton equates to 12,000 BTUs. So for example, if you have a 3-ton air conditioner or a heat pump, that means it has an output capacity of 36,000 BTUs, 3 times 12,000 per ton. Now back to my big equipment analogy. For decades, many AC contractors determined the size of AC units needed by simply taking the total square footage of the house and dividing it by 4 to 500. For example, if your house was 2,000 square feet, they'd say it needed a 4 to 5 ton AC system. There was no building science taken into account for these calculations, and no good logic behind the 4 to 500 range given either. So no matter how leaky or tight the house was, or how well or poorly insulated it was, or how much shading was on the house, most contractors just assumed they all needed the same size equipment, which obviously wasn't correct. The same basic thing happened when installing heating systems, which led to a lot of homes having oversized heating and cooling equipment. And that problem is still prevalent to this day in the HVAC industry, unfortunately. Bigger systems may sound appealing and are often promoted to homeowners by contractors who don't know any better as the solutions to their comfort problems. But oversized equipment tends to short cycle and can cause more problems than it could possibly help. Remember, short cycling is when the system turns on and off frequently, which wastes energy, reduces comfort, and doesn't effectively manage humidity in cooling seasons. Undersized equipment, on the other hand, can struggle to maintain the temperature you set your thermostat to, leading to unnecessary wear and tear as it works overtime. The key here is choosing the right size system based on proper heating and cooling load calculations for your house, not just a guess based on old ways of doing things. These calculations don't have to be perfect to make a big difference, but they should at least account for how leaky the house is, how well insulated it is, and any natural shading provided by nearby buildings or trees. A little extra effort on the front end here goes a long way in the end. Next, we're going to discuss the types of HVAC systems. There's really no one-size-fits-all solution when it comes to HVAC systems, and many times the right system depends on the climate zone you live in, along with the type of fuel you have available to you, and how well insulated and air-sealed your house actually is. Here's a rundown of the main types of HVAC systems: gas furnaces, air conditioners, heat pumps, geothermal systems, and boilers. Let's start with gas furnaces. Gas furnaces are extremely common in northern, colder states, as well as the middle of the country. They put out a lot of heat, and that air temperature is usually between 120 and 140 degrees. They can be powered by natural gas or propane, and no matter which fuel source they use, these systems require oxygen in order to burn the fuel properly and work efficiently, which is why they're referred to as combustion appliances. There are basically 2 efficiency classes for furnaces based on their combustion efficiency: 80% AFUE and 90% AFUE or higher. AFUE stands for Annual Fuel Utilization Efficiency, and these higher efficiency units can go up to 98%. They also use white PVC pipes to remove the flue gases from the systems directly to outdoors, rather than the large sheet metal flue pipes used on 80% furnaces. 80% systems are referred to as open combustion or atmospherically vented systems. 90% and higher systems are called direct vent, sealed combustion, or condensing systems. Let's talk about open combustion systems. These pull the oxygen needed to burn the fuel from inside the home or wherever the equipment is actually located. So if your furnace is located in a garage, an attic, or a crawl space, then the oxygen needed comes from that garage, attic, or crawl space. Specifically, these systems require 50 cubic feet of air per 1,000 BTUs of heating output they produce. So it's important to know whether or not the space the equipment is located in has access to that much volume of air. For example, if you have an 80,000 BTU open combustion furnace located in a room in your basement that is 8 feet wide by 10 feet long and 8 feet tall, then that room has 640 cubic feet of air by itself. Then you divide 80,000 by 50 to get 1,600 cubic feet of air needed for that system to work properly. Obviously, 1,600 is way more cubic feet needed than the room provides alone, so in these situations, you either need to install a louvered door on the HVAC room or install a transfer grill through a wall of that room so that the system can pull more cubic feet of air from the rest of the basement area surrounding it. Keep in mind that if there is also a gas water heater in that same basement room that is also an open combustion type, you have to account for the extra volume of air needed for the water heater to operate properly when the furnace is also running at the same time. Sealed combustion systems should pull their combustion air in directly from outdoors and always vent flue gases directly outdoors. Many times these systems do not have their intake pipes run outside the house and instead just pull combustion air needed from the surrounding area, just like open combustion systems do. If you have the space and the ability to run those pipes outdoors, you should always do it to reduce the chances of combustion issues and other health and safety problems that may arise from a lack of combustion air. Next, let's discuss air conditioners. AC systems are what keep your house cool in the summertime, and they should dehumidify the air inside as well. They use airflow to move indoor air past a cold coil with refrigerant inside it to cool down the air, and that heat inside the air is moved through the refrigerant line to the outdoor unit called the condenser, which releases the heat into the outdoor air. There's basically two types of AC systems you'll see most often: central AC systems connected to ductwork, and window or room AC units that stand alone. There's a third type of AC that is only found in hot, dry climates called swamp coolers, but for the purpose of this course, I'm going to leave that one out for now. Central AC systems are usually paired with a gas or propane furnace connected to a duct system and have an air filter to help reduce dust, pollen, and other allergens from circulating throughout the house and clogging up the HVAC equipment. These are the most common ones out there, and it's very important that they get the proper amount of airflow through them for the size of the equipment you have to maximize efficiency, cooling ability, and dehumidification. Window or room AC units are common in houses without central AC, but they're also often used to supplement a central AC system that isn't working well enough to cool certain rooms in a house. They usually don't have good air filtration systems like central AC units do. And if this sounds like your house, it's a good sign that you have another issue that needs to be solved, like air leakage or a lack of proper insulation surrounding the problem rooms. Although it can certainly also be an issue with the AC system or the airflow moving through the ductwork to that room. I'll discuss more about ductwork issues in the next chapter. The air temperature out of most AC systems will be between 50 and 60 degrees. Anything colder or warmer than that is an indication that something isn't working properly and may need to be checked on by a pro. But the first place to look is for a dirty air filter that needs to be replaced. Dirty air filters reduce airflow, and lower airflow in AC systems means colder air comes out, which can freeze AC components and cause damage over time. Next up are heat pumps. A heat pump system is basically an air conditioner that works to move heat in both directions, depending on the season. In the summertime, it works just like any other air conditioner to move warm air outdoors, but in the wintertime, it can actually pull heat out of the cold outdoor air and move it back indoors, even down to single digits outside. There are two common types of heat pumps: ductless heat pumps, which are also called mini splits, and traditional ducted heat pumps. Mini-split heat pumps are an efficient and flexible alternative to traditional HVAC systems. Unlike ducted heat pumps, mini-splits consist of an outdoor unit connected to one or more indoor air handlers. These indoor units are mounted on walls or ceilings and directly heat or cool individual rooms or zones. One of the biggest advantages of mini-split heat pumps is they're very energy efficient, and many models offer advanced inverter technology, which also allows them to fully adjust their output based on incremental demand, further improving efficiency and comfort. Mini-splits are an excellent solution for homes without existing ductwork, room additions, bonus rooms above garages, or in large open areas that may need extra heating or cooling. They also provide zoned temperature control, allowing you to customize temperatures in different rooms. Although these systems are not very popular in North America compared to the rest of the world, they're becoming more popular every day. While mini-split heat pumps offer many benefits, there are some drawbacks you need to consider. One significant limitation is their lack of advanced filtration options. Unlike ducted HVAC systems, which can accommodate high-efficiency air filters or home air purifiers, most mini-split systems have only basic washable filters. These filters primarily trap larger dust particles, but do little to improve indoor air quality by removing allergens, pollutants, or odors. Homeowners with allergies or respiratory concerns may find mini-splits less effective at maintaining clean indoor air. Another challenge is maintenance and cleaning with these. Mini-split air handlers accumulate dust, mold, and other contaminants over time, particularly on the blower wheel and evaporator coils. But unlike central AC systems, which have accessible ductwork that can be cleaned periodically, mini-split units require more intricate cleaning procedures. Homeowners often overlook this maintenance, leading to reduced efficiency, musty odors, and even health concerns due to mold buildup. Professional cleaning can be expensive too, and DIY cleaning can be difficult without specialized tools. Additionally, mini-split heat pumps tend to have a reduced ability to dehumidify indoor air compared to traditional central air conditioning systems, and this is especially problematic in warm, humid climates. Some models have a dry mode to help with dehumidification, but it's not as effective as a dedicated dehumidifier or a properly sized central AC system. This can lead to higher indoor humidity levels, which may contribute to discomfort, mold growth, and indoor air quality issues. While mini-splits are an excellent choice for many homes, you have to consider these potential issues when deciding whether they are the best solution for your particular needs. Heat pumps are most often used in warmer climates, especially in the South and Southwest United States, but they can work in northern states as well, depending on the following conditions. The house is air sealed well and insulated reasonably well. There is a backup heat source for emergency situations when it gets extremely cold or the heat pump condenser outside stops working. These are usually electric heat strips or a gas or propane furnace, which is referred to as a dual fuel system. I'll talk more on that here in a minute. The third condition is that the system and/or the ductwork is ideally located inside the living space of the house. Now let's discuss hybrid or dual fuel systems. These are a combination of a heat pump and a natural gas or a propane furnace, with the heat pump supplying most of the warm air throughout the year. During normal defrost cycles and when the temperatures get really low outside, the heat pump will switch over to the gas furnace to supply the heat. These are great options for those who live in northern climates who want high efficiency systems and the extra safety of having a gas backup when it's needed. Geothermal systems are up next. Geosystems use the Earth's heat underground to transfer heat from inside your house back and forth. They're referred to as ground-to-air heat pumps if they're connected to a duct system, and ground-to-water heat pumps if a radiant heat system is used. Geothermal systems are the most expensive type of HVAC system you can install, but when they're done correctly, they can last for 20 to 30 years versus 10 to 15 years for most other types of systems. They also currently qualify for federal tax credits, and some states also offer local incentives, so be sure to check with your local utility and state energy office for more details. There's a lot of debate about geothermal systems versus heat pumps for energy efficiency, cost effectiveness, and ease of maintenance. In general, you can get pretty equal efficiency out of both types of systems today, with the edge going to geothermal systems, but they also require more skilled labor to install them correctly. If the ground wells or loops aren't sized and installed correctly for geothermal systems, then that system will never operate as efficiently as it should. The same goes for the sizing and design of the duct systems with heat pumps and any other forced air heating and cooling equipment. We'll talk more on duct systems in the next chapter. Next up is boilers. These systems are ideal for radiant heating systems, and there are different fuel sources for them depending on what your local utility company provides. Boiler systems are used with radiators located in each room of the house or with in-floor heating systems, and they're more common in the Northeast U.S. and in older housing stock in general. I personally don't have a lot of experience with boiler systems because they're not very common in the Midwest where I live and work, but the things I like about boiler systems are that it gives you warm, consistent temperatures across the home, and they don't contribute to the air leakage and heat loss in your home like forced air systems can do. Now let's compare forced air distribution versus radiant heat. Forced air systems like those with a furnace or a heat pump push air through ductwork to distribute heating and cooling. Radiant heat, on the other hand, warms objects and surfaces like heated floors or old-school radiators. Forced air is faster and it works with a central AC, while radiant heat provides even, consistent warmth and can also provide the hot water for the house, but it doesn't actually provide any cooling. Now let's discuss single-stage versus multi-stage output systems. Single-stage systems are either 100% on or off. There's no in-between with those systems. Most HVAC systems in operation today are single-stage systems, and that's probably what's in your house right now. Multi-stage systems, on the other hand, adjust their heating and cooling output to meet the home's heating and cooling demand as outdoor temperatures change. Multi-stage systems run longer throughout the year, which distributes the air more evenly to all the rooms, removes more moisture during cooling mode, and provides more air filtration year-round because of the longer run cycles. These things make them more efficient and healthy overall versus single-stage systems, and I highly recommend getting one when you have the opportunity to upgrade your heating and cooling equipment. Now let's discuss fixed-speed blowers versus variable-speed blowers. Blower wheels are what move air through a forced air HVAC system. They kind of look like a hamster wheel inside your furnace or heat pump air handler. Fixed-speed blower wheels run at one constant speed and have PSC motors, which stands for Permanent Split Capacitor. Their control panels can be adjusted to higher or lower motor speeds to move more or less air as needed, but they don't automatically adjust speed based on output demand like ECM motors do with variable speed blowers. ECM stands for Electronically Commutated Motor, and these are paired with variable speed blower wheels and multi-stage HVAC equipment. If you have a single-stage gas furnace with a PSC motor and want to replace your current AC system with a new multi-stage AC or heat pump, your current gas furnace won't be compatible and will need to be replaced as well. So anytime your furnace goes out before your AC or heat pump system, make sure it's replaced with one that has at least 2 stages of gas heat output and a variable speed blower for future compatibility. Next up are air conditioning and dehumidification. As we discussed back in Chapter 3, air conditioning isn't just about cooling the air inside your home. It's also about controlling humidity as well. Too much humidity in the air can make a home feel warmer than it is in the summertime and clammy in the wintertime, and can also lead to issues like mold growth. Properly sized AC systems help maintain a comfortable relative humidity range of typically between 40 to 50% year-round. Some newer AC systems even include dedicated dehumidification features, so be sure to ask your HVAC contractor about these options if you're considering an upgrade. Next up are air filtration options. Indoor air quality matters, and filtration plays a big role in that. From basic furnace filters to high-efficiency options, wider media filters and electronic air cleaners, there's a lot of options to choose from, and those choices can frankly be overwhelming. Most people with forced air HVAC systems have a 1-inch thick air filter that they use. There's a lot of companies marketing high efficiency and allergen reduction air filters to consumers, and those filters have high MERV ratings, which means they catch more junk as air moves through them. The problem is 1-inch thick air filters with high MERV ratings usually are more restrictive than most systems can handle, so they end up reducing airflow, efficiency, and equipment output as well. What happens is a pressure drop occurs across the air filter when the blower wheel is on, and if the filter is too restrictive, the pressure drop will be too great and can cause the AC coil to freeze up due to lack of airflow across it. The same thing can happen with heat exchangers. Unless you've had a professional test the pressure drop across these type of air filters in your own system, I would stay away from them and just buy cheaper ones that are MERV 8 or less and replace them every month or so. A better option for air filtration is installing a media filter rack to replace your 1-inch thick filter rack. Media filters are usually 4 or 5 inches thick and provide a lot more surface area for the air in your ductwork to move through, which also means more surface area to filter out dust and other junk inside your air. These types of filters don't cause the crazy pressure drops found with equivalent high MERV 1-inch thick filters, and they're a relatively inexpensive option to upgrade most systems out there. Electronic air cleaners for HVAC systems are high-end filtration options and the most expensive option available. Depending on the type, some can kill just about anything that moves through them, so they're often used in hospitals, industrial, and commercial buildings, as well as in homes where homeowners demand the cleanest environment possible. However, I personally don't think most people need these types of air filtration systems, and I generally recommend properly sized, high MERV media filters instead. Now let's discuss humidifiers. When the air gets too dry inside your home, which is generally in the wintertime, a good humidifier can help out a lot. Humidifiers add moisture back into a home's air by mixing water vapor with the airflow in your HVAC system to regulate the relative humidity indoors. This helps prevent issues like dry skin, eyes, and sinuses, reduces static electricity, and even helps prevent damage to wood floors, trim, and furniture, since wood expands with higher humidity and contracts with lower humidity. Low humidity is also one reason why you'll see the trim in your house separate from walls and ceilings, and doors get harder or easier to close or open depending on the season. The most common type of whole house humidifier is called a bypass humidifier because it connects to the supply and return side of the ductwork, bypassing the regular flow of air through the system. Whole house humidifiers also have filters inside them that degrade over time, and usually you'll have to replace them once a year. If you don't replace the filters and make sure that the drain line stays clear, they can clog up and cause the humidifiers to stop working, so be sure to check them every year. Now let's talk about fresh air options for your home. Providing controlled fresh air has been another hot topic over recent years and has even been included in many states' building codes, but there's a lot of debate about whether or not this is truly needed for most houses. Essentially, the argument comes down to this. As newer homes are built to be more airtight and better insulated than in the past, the theory is that mechanically controlled fresh air is needed to provide good indoor air quality for the occupants and avoid causing issues like mold or mildew growth. The problem with this logic is that good indoor air quality starts first and foremost with proper dehumidification of the air inside your home during the cooling season. And if the AC system isn't sized properly to begin with, it's never going to dehumidify the air properly in the first place. If that's the case and you add fresh air from outdoors into your home in the summertime, you're actually going to add more moisture into your home that also needs to be dehumidified, making the problem even worse. There are two other issues with providing mechanical ventilation. One is most homes today are not built tight enough to truly warrant this need. And the other is there are 3 types of mechanical ventilation available and acceptable to meet these code requirements, but those 3 types perform very differently from one another. The 3 types of mechanical ventilation are supply air, balanced air, and exhaust air. Supply air is typically with something called an air cycler, which is a duct that runs from outdoors and connects to the return side of your duct system. It should have a damper installed to close the duct when not needed, and that damper can be opened automatically when the HVAC system runs, or have its own fan that pulls in air through it. These systems can positively pressurize a house, which is preferred over depressurization, which means sucking air into the house through gaps and cracks in the pressure boundary. Exhaust air is basically a fancy exhaust fan that runs either continuously at a certain airflow rate or intermittently at a higher rate. These fans have low SON ratings, meaning they are very quiet, and they have DC motors for efficient operation. These systems can depressurize houses and are the least expensive and effective option for improving indoor air quality. The third option is balanced air. These are ERV and HRV systems, where air is pulled into the house through a duct, kind of similar to the air cycler previously mentioned, but air is also exhausted outdoors through the same equipment. Since air is both pulled into the house and exhausted out, that's why they're called balanced systems, and ideally they should not pressurize or depressurize the house, but improper installation can cause this to happen anyway. ERV stands for Energy Recovery Ventilator, and these are primarily used in the Midwest and South U.S. where humidity is more of a concern. They will remove some moisture from the incoming air, but they will still add humidity to homes located in humid climates. They are often mistakenly used as a band-aid in homes with humidity problems instead of focusing on the AC equipment size or installing a dedicated whole house dehumidifier. HRV stands for Heat Recovery Ventilator, and these are more often used in northern cold climates and homes that are substantially airtight. They can capture some of the heat in the air leaving the house and prevent some of the cold air from outside from entering the house in the first place. At the end of the day, it really comes down to knowing how tight your house is and whether or not your AC system is sized properly in the first place. If the relative humidity inside your house is between 40 to 50% year-round, and you're not experiencing other air quality issues like dust or allergens, then I wouldn't worry about adding mechanical ventilation. If you do have high humidity levels in your house and your AC system is already sized properly, the better option in my opinion would be to install a dedicated whole house dehumidifier instead. The last thing we're going to talk about are thermostats. Thermostats play a crucial role in controlling HVAC systems by regulating indoor temperatures based on user settings and outdoor weather conditions. Several types of thermostats are commonly used, and each type offers different features and levels of efficiency. The first type are manual or non-programmable thermostats. These are the most basic type of thermostats available, and they can either be analog or digital thermostats. They simply allow you to set the temperature you want inside your home, turn the blower fan on or off, or turn the HVAC system on or off. They do not offer scheduling or automation options, but they're reliable and relatively inexpensive. Basic digital thermostats are more accurate and energy efficient than analog ones as well. The next type are programmable thermostats. These allow users to set temperature schedules based on their daily or weekly routines. For example, you can program different temperatures for when you're at home, asleep, or away from the house. They can improve energy efficiency by adjusting temperatures automatically, potentially reducing heating and cooling costs. The setup and programming of some thermostats can be confusing and counterintuitive though. Choosing one that's easy to use and program will ensure that it actually gets used as intended. The third type of thermostat is a smart thermostat. Smart thermostats connect to your internet via Wi-Fi and offer advanced features like remote control via smartphone apps, learning user preferences, and integrating with home automation systems too. Some popular brands include Nest, Ecobee, and Honeywell. These thermostats can maximize energy savings by learning occupant habits and adjusting temperatures accordingly. They offer remote access, and they can even integrate with voice assistants like Siri, Google, or Alexa. Smart thermostats are also the most expensive option, and they may require a C-wire or professional installation in some cases, but they're usually pretty simple to install on your own. The fourth type of thermostat is a line voltage thermostat. These are typically used for electric baseboard heaters and other high voltage heating systems. Unlike low voltage thermostats used in central HVAC systems, line voltage models operate at 120 volts or 240 volts. Overall, they have limited functionality compared to programmable or smart thermostats. The next one up are wireless and zoned thermostats. Wireless thermostats communicate with the HVAC system without hardwired connections, while zone thermostats allow different areas or zones of a home to be heated or cooled independently. These are often part of a smart thermostat system where additional sensors and controls can be added for extra control. They provide precise temperature control in different zones and can improve comfort and efficiency as long as the HVAC equipment and duct system is designed properly for zones. We're going to talk more on this in the next chapter on duct systems. Zone systems can be expensive to install and in many cases are used as a band-aid for poorly air-sealed and insulated houses. In my opinion, I'd rather focus on fixing the causes of comfort issues before considering adding zone controls to an HVAC system, because that also generally requires multi-stage equipment with variable speed blowers. The best thermostat depends on your particular HVAC system, lifestyle, and budget. If energy savings and automation are priorities, along with the ability to control your system remotely from your phone, then a smart thermostat's what you want. For those who prefer simplicity, a programmable digital thermostat is fine for most systems. For anyone using less than a basic digital thermostat, consider upgrading it before you replace your HVAC system. And if you're going to install a new high-efficiency HVAC system, you'll probably have to upgrade to a smart one anyway to take full advantage of all its new features and settings. My personal favorite smart thermostat is the Ecobee 3 line, which is similar to the Nest with more features and controls, and an easier to use interface overall for about the same price. You can even add extra sensors for different rooms, track air temperature and relative humidity with each of those sensors over time, and even track system runtime as well. All that data can be exported too, so you can really see how your house is performing year-round. Most people won't use the export feature, but it's nice to have that data and share with your HVAC company in case there's any comfort issues that you experience. One other really cool thing you can do with runtime data is see how long your heating and cooling system runs during the most extreme temperatures each year. Your HVAC system is usually sized based on temperatures on those worst-case days in summer and winter time, referred to as design temperatures, and they depend on the climate zone your house is located in. If your system is sized correctly, it should be running for 50 to 60 minutes of every hour when the outdoor design temperatures are met. If your system only runs for 20 to 30 minutes at a time, then it's likely oversized and short cycling most of the year. It's far more rare to find undersized heating and cooling equipment versus oversized, so this is one easy way to tell how well sized your current system is. So there you go. That was a high-level overview of HVAC system types, features, and some upgrade options for you to consider. In the next chapter, we'll be talking about the importance of duct systems and how the air gets moved throughout your house. I'll see you in the next chapter soon.